Hi, my name is Kira Lamro, and today we're going to talk a little bit about tyrosinase kinetics, specifically with and without the presence of the inhibitor kojic acid. Tyrosinase has been found in many different natural sources and is commonly known to be in mushrooms and human melanin, but is also found in other fungi, fruits, and mammals. Tyrosinase, formerly known as monophenol monooxygenase, and in our experiment is from the mushroom Agaricus bisporus. Enzymes are simply proteins that catalyze a biochemical reaction. So understanding this, what tyrosinase does, how it kind of helps produce this melanin, which we'll talk a little bit more about in the next slide, we can have a purpose to study tyrosinase and their kinetics. So if we can understand how tyrosinase works kinetically and how it's affected by inhibitors, we can help develop drugs that would slow hyperpigmentation or slow the production of tyrosinase and melanin production. And that could help people who have hyperpigmentation or problems with their melanin. So SDS was used in this experiment so that we can activate the tyrosinase so that we can see if there's a change in absorbance over time. So this is just going to allow us to see how the enzymes are working together, how the inhibitors are working, just so we can see how all of the kinetics work. The inhibitor that we specifically used in this experiment was 2.4 millimolar kojic acid, and this inhibitor specifically is known to inhibit both monophenolase and diphenolase activities. So how we mentioned before, tyrosinase is in a lot of living organisms, but one of the things that we're focusing on is its role in pigmentation in humans. And so tyrosinase itself is an enzyme, so it's a protein that's going to catalyze a reaction called melanogenesis, which in the end is a pathway that produces melanin. And so this enzyme can also function in a couple different ways. So it also works in blanded adhesions, wound healing, defense against stress, dehydration, and extreme temperatures. So it's important for a lot of things. It's also known to catalyze a few different reactions, two of which are the hydroxylation of monophenols, which is known as cryolase activity, and the oxidation of diphenols, which is catecholase activity. The active site of the tyrosinase in our mushroom is a binuclear copper binding site. These are usually referred to as copper A and copper B, or CUA, CUB. It's because of these binding sites that tyrosinase is able to perform both monooxygenase and the oxygenase activities. Some substrates that interact with tyrosinase include tyrosine, tyramine, 4-hydroxyanisyl, MBTH, 4-methylcatechol, catechol, DL-dopa, dopamine, chlorogenic acid, T-butylcatechol, and catechin. There are also a few potential products that tyrosinase can produce. However, its ability to produce melanin through melanogenesis and L-dopa through its catechol reactions are some of the most sought-after products. Many isozymes of tyrosinase exist. A few of the ones that are involved in the early stages of the biosynthesis of melanin include L-tyrosine, cysteine L-dopa, 2-dopaquin, 3-cyclodopa, cysteine L-dopa, quinone, 4-dopa, and 5-dopachrome. While they have the same molecular formula, they have different chemical structures, which makes it more complicated to test for tyrosinase due to the conformational changes and the possible aggregation of the monomeric units. There's a whole bunch of inhibitors that can be used to affect tyrosinase. But once again, the one that we're going to be using today is kojic acid. And all of this activity can be regulated by those inhibitors. So as soon as you add any inhibitor, it's going to affect how the whole reaction works. So for example, with alpha-arbutin, this competitively inhibits tyrosinase activity. Kojic acid, both non-competitive or competitive, non-competitive, mixed type inhibited diphenolase activity. There's also the beta-arbutin, which both non-competitively and competitively inhibit monophenolase activity. Okay, so this is our first figure, and this represents all of the trials of the raw absorbance data that was taken of the tyrosinase in the presence of SDS and catechol. So we were just measuring what the normal absorbance of tyrosinase is. Excuse me. And here we occluded trial 2 and trial 8 because they didn't fit on the graph and it really didn't make any sense. So we still have 6 data points, just to know that 2 of those were occluded. And then here, figure 1b, is the absorbances with versus without the inhibitor. So we can see that the orange data represents the uninhibited enzyme, so the information that we just had on the previous slide. And then the blue points represent the absorbance in the presence of the kojic acid. So as we can see, the blue line is a lot lower than the uninhibited tyrosinase. And so this is because that kojic acid was introduced. And so we'll talk a little bit more about this in the following slide. Okay, so here's our first table, table 1. And here it's going to show that trial number, the amount of catechol, and the relative activity with or without the inhibitor. So without the inhibitor, we used quite a bit less catechol in millimoles. And so we started out with 4, and then it cuts in half every time. So 4, 2, 1.5, and so on and so forth. And it follows the same trend with the catechol with the inhibitor. So it starts out with 12, and then each time it goes down, it's cut in half. And this is to allow us to be able to see a clear graph about how the inhibition is, or how the kinetics of the tyrosinase are being affected by the inhibitor. And so we can see that the general trend is that as there's less catechol, the relative activity also falls. And this goes throughout. We can see in trial number 8, for the catechol with the inhibitor, there's some kind of wonky numbers there at the end, but for the most part, it follows this trend that it's just decreasing while the catechol is also decreasing. Okay, so here we have an 80-Hofstee plot, and this is basically a way of plotting kinetic enzyme data so as to yield a straight line for reactions obeying the Michaelis-Menten kinetics. So the velocity of the reaction is plotted on the vertical axis, or the y-axis, and it's as a function of the V over S ratio, or the substance ratio, on the horizontal axis, with S being the initial substrate concentration. So based upon the line patterns of this plot, we can guess as to what type of inhibitor is affecting an enzyme. So if we already have this information, or we got our data, as we can see from the previous slides, then we just put it onto this 80-Hofstee plot, and we can see a lot easier what kind of inhibition is happening here. So we can also see, I just want to point out a few things. So the line of best fit for the blue line is y equals negative 0.5201x plus 68.607. And then the R squared value is going to be 0.8749. And then the orange line, which is going to be the one with the kojic acid inhibitor at the 2.4 millimole concentration, that line of best fit is going to be y equals negative 0.6967x plus 39.814. And then the R squared valued is going to be 0.7057. And then the inhibition constant, or that Ki that was found, was 3.319 about molar. So that it really shows us quite well that when the inhibitor is added, the Km drops, the V drops, everything is decreased quite significantly. So here in table 2, we are seeing all of the summaries of all the estimations for Vmax, Vmax over Km, and Km for the tyrosinase at pH 7. And then we are seeing it with inhibitor and also without the inhibitor. So a few things to note here. We can see that without the inhibitor, the Km was lower than with the inhibitor. So that Km increased. We also see that the Vmax was significantly higher without the inhibitor than it was with the inhibitor. So Km, I'll just kind of explain what these things are. Km is a concentration of substrate which permits the enzyme to achieve half of Vmax. And this figure, in the figure previous, the slope is the negative Km. Vmax over Km is the y-intercept. And Vmax is the reaction rate when the enzyme is fully saturated by the substrate, indicating that all the binding sites are being constantly reoccupied. In the previous figure, it was the y-intercept. So these uncertainty estimates just show the degree of variance that the Vmax and the Km can have. It's also seen that it really varies. So for example, the Vmax uncertainty estimate without the inhibitor was almost 8.5, whereas the Km uncertainty estimates were barely 1.3, 1.4-ish. So those varied slightly. Okay, so let's kind of talk about all of the results. So once again, just kind of restate the objective. If we're able to slow the kinetics of tyrosinase, we are then able to maybe help people who have hyperpigmentation, and we can slow the production of melanin by slowing the kinetics of tyrosinase. So is this experiment a success? The results that yielded a graph that represented an uncompetitive inhibitor, which is not at all what we expected. We were desiring a competitive inhibitor. So that was kind of an unexpected result. While we did end up having that uncompetitive inhibitor, we did see a really large inhibition of tyrosinase when the kojic enzyme was present. So this is what we expected, which is pretty reassuring. So for the most part, the data was good quality. All of the lines fit together, just excluding that trial 2 and trial 8, excuse me, from the uninhibited tyrosinase experiment. So those are the only 2 data points that we threw out. Otherwise, everything fit pretty well. So in the presence of the inhibitor, the Vmax value dropped significantly, which was seen in table 2. However, the Km value increased slightly. So this can be seen in, once again, table 2, and can be seen in figure 2 because the negative Km value is represented by the slope of the Eadie-Hofsky plot. The Ki value, or the inhibition constant that was found, was 3.3186. I wasn't able to find anything in any literature about a Ki, but I was able to find information about Km. So according to the literature that I found, the Vmax of kojic acid remained a constant and the Km increased when the concentration of kojic acid increased. The Km found in this experiment also increased. However, the Vmax was cut almost in half, which is super different from what the literature said. Kind of in summary, kojic acid most definitely inhibits tyrosinase and can be used to slow the proliferation of melanin in a cell. However, there would need to be more tests performed to see how the kojic acid affects a cell and if it would be safe treatment for hyperpigmentation. So as in most experiments, there was uncertainty, as we could see in figure 2. So those estimates provide an interval of values within which we think that the true value probably is, but it was a huge, huge, huge uncertainty constant. So that was super good. And there are some references, but thank you so much for listening to my presentation about tyrosinase kinetics. And yeah.